Good morning, everyone. My name is Hassan Idris, and I am an electrical engineer at Jacobs Engineering in Denver, Colorado. Together with my co-presenter, Mr. Donald Kinsella from the city of Omaha, I will be presenting on arc flash studies for asset management of lift stations. Owing to some conflicts, I was unable to be physically present today to deliver this presentation, and so Don and I will do our best to field questions. Here is an outline of our presentation today. We will give a background about condition assessment project that necessitated this arc flash project at wastewater facility sites across the city of Omaha. We will explain what arc flash means and take a look at arc flash hazards at water and wastewater facilities. There are slides that will touch upon the electrical codes and standards that drive these studies, followed by arc flash analysis, including understanding electrical one-line diagram and protective device coordination curves. Finally, we will look at arc flash labeling and what that means for worker safety. Back in 2022, Jacobs documented the risk and current physical condition of the sanitary lift stations owned by the city of Omaha at an asset and station level for the purpose of managing risk by prioritizing O&M and capital improvement needs for budgeting and planning. The purpose of this effort was to assist the city of Omaha as they continued to close out their CMOM or capacity management, operation, and maintenance gaps for these lift stations. The graphic on the right demonstrates a risk-based approach for asset management where the top-down facility level activities drive the bottom-up element level actions, which together in a cyclical fashion refine the capital planning and maintenance activities. The city established several foundational elements of a formal asset management program. These elements include those identified on the left. The first was identifying station services areas using GIS. Then the existing CMMS system was leveraged using IBM Maximo. Validation of asset registry was the next step. This was followed by realization of current asset status, asset deficiency prioritization, and risk-based assessment and prioritization based on a standardized process, as well as a maintenance approach. Other elements included transparency with regulators, data quality, the basis of system health and management reports to support repair and workload projections, capital upgrade projections, staffing projections, etc. The chart on the right shows the result of that assessment. The lift stations with lower risk score, for example, 13th and Carter Boulevard, are on the left, and those with higher risk scores, for example, 16th and Pershing, are on the right. One of the major recommendations from this assessment included arc flash studies for the lift stations, which brings us to this topic. The question now is, what exactly is arc flash? And the answer is that arc flash is mainly a discharge of energy. It is the sudden release of energy, electrical energy to be more precise, through the air following a phase-to-phase or phase-to-ground electrical fault. During an arc flash event, electrical current flows through ionized air and causes a tremendous sound, pressure, and light impact as electrical energy is converted into other forms of energy. To give you an idea as to how hot arc flash incidents can get, within a millisecond, temperatures can reach 35,000 Fahrenheit, which is actually 4 times hotter than the sun. However, this high temperature lasts for a short time duration only. To drive home the point as to why arc flash incidents can be dangerous, here are some facts. Fiery explosions because of arc flash can result in serious damage to workers and to electrical equipment. According to the National Fire Protection Association, or the NFPA, 5 to 10 arc flash incidents occur every day, and more than 2,000 people are treated annually in burn centers with arc flash injuries as of 2023. An engineering company in the US has estimated 400 fatalities per year due to arc flash incidents. And then there is the financial impact in the form of fines, lawsuits, and damages. According to one expert, the average medical expense for an employee who survives an arc flash is $1.5 million. The price of litigation and settlement in arc flash cases is between $5 to $10 million. Imagine this. During a severe arc flash incident, within the span of milliseconds, there is a lot of stuff coming out from that electrical enclosure. There are blast pressure waves at 140 decibels that can throw workers or operators across rooms. There is molten metal shooting at speeds exceeding 700 miles per hour and propelled up to 10 feet. Basically, there is a sudden and severe impact from light, sound, pressure, heat, and metal. And a lot of this is actually avoidable. Here is a sobering fact. Around 30,000 arc flash incidents occur every year, and 5 to 10 arc explosions occur in the US every day. Experts indicate 2 out of 3 incidents result from inappropriate action of a worker and/or a lack of proper direction. Surely there is something that we can do to eliminate these incidents. Take a look at the garments of a worker after an arc flash incident. The injuries from arc flash incidents can potentially span second-degree and third-degree burns, severe damage to the respiratory systems, possible blindness, vision and hearing impairment, and skin ruptures from flying debris. Other impacts include severe damage to electrical equipment, delays and downtime caused by OSHA investigations, which can further hamper productivity and operations of a water or wastewater facility. Aside from that, attracting and retaining qualified technicians can be difficult if an arc flash incident causes existing and prospective employees to view the facility as an unsafe place to work. Speaking about financial havoc, here are a few examples of OSHA fines. PAI Industries was fined $55,800. Nissan Brakes in Georgia was fined $53,000, and McAfee Electric in Florida was fined $51,000. This is aside from the people and equipment damage that these companies incurred. As indicated previously, protecting the workers operating energized and de-energized equipment is one of the most important aspects. And a paramount reason why we embarked on this project with the City of Omaha is, of course, ensuring personnel safety of those working in and around the equipment, in compliance with electrical and fire safety standards and regulations. Arc flashes can result in severe injuries or fatalities, and understanding the potential risks helps in implementing proper safety measures. OSHA and NFPA mandate adherence to specific safety guidelines, including arc flash assessments and risk mitigation strategies like PPE, equipment modifications, and changes in work procedures to minimize the risk of arc flashes. Since arc flashes can cause significant damage to electrical equipment, understanding the potential risks and implementing preventive measures protects valuable assets, preventing costly downtime and repairs. By addressing arc flash hazards, the city is improving the reliability and continuity of operations at their wastewater infrastructure, avoiding unplanned outages and disruptions. The work plan for these studies followed this process. The first step was to apply the relevant sections of codes and standards that were driving the study. This includes NFPA 70E, Standard for Electrical Safety in the Workplace, IEEE 1584 Guidelines for arc flash calculations, and the evaluation method. The second step was to collect the necessary data, including working with the Omaha Public Power District, or OPPD, which is the electric utility, for transformer, voltage, current, and fault information. The site visits, including obtaining data on breakers, fuses, circuit protectors, disconnect switches, their types, models, manufacturers, strip settings, etc., conductor sizes and lengths, and electrical enclosures. After the site visits, the data was compiled to generate an arc flash model using SKM Power Tools for Windows, and other analysis efforts were rolled into this arc flash evaluation. The final step was report documentation and arc flash labeling on equipment. To calculate the incident energy from an arc flash, we used standardized working distance, duration of arc, and three-phase voltage fault current. NFPA 70E incident energy equation calculates the arc flash energy in calories per centimeter squared. The arcing current in kiloamps is calculated from the IEEE 1584 arcing current equation using a constant value, fault current, bus voltage, and conductor gap. This allows the correct selection of protective devices like circuit breakers. The NFPA 70E standards helps us understand what PPE operators should wear, and the IEEE 1584 standard helps in calculations. When used in design, this can help reduce fault current, shorten arc flash clearing time, and enable an arc flash reduction maintenance system in a variety of design software. Here is a look at an example one-line diagram with a time current coordination curve. You can take a look at how the utility connects different components all the way to the different loads. The graph on the right shows the 3 or 4 different protective devices and how they're current coordinated to be able to protect the load as well as other components in the electrical power distribution system. The design software can then enable printing of the super informative arc flash labels, which help keep workers safe, inform them about potential workplace electrical hazards, and how to operate energized equipment. For more traditional workers, wearing the correct PPE as per the incident energy levels enables protection, which includes both clothing and protective equipment. The arc-resistant clothing protects workers from burns and provides a solid line of defense, and this provides a level of protection more advanced than the regular protective equipment. Typical industry hazards include visual and infrared inspections, manipulation of live conductors, switching and racking breakers, removal and replacement of live components, replacement of fuses and links, live underground cable jointing, and installation of cables into energized equipment, as well as inadvertent energized equipment penetrations. Increased risks include poor equipment maintenance, poor or old equipment design and installation, poor equipment commissioning and initial inspection, poor worker competence, human error, and lack of concentration and absence or presence of distractions. Sometimes it is necessary to work on live equipment, and so if operators find themselves in that situation, it is essential that they get robust answers to these questions. Two of the more important things are making sure that proper work procedures exist and that an engineer has performed safety and arc flash hazard analyses in advance of working on that live equipment. In today's environment, where there are better procedures available to us, using remote operation, and this includes robotic equipment for operating and opening electrical gear, is very helpful. Similarly, Using infrared windows in thermography using insulated tools and keeping an arc blanket handy can reduce arc flash in live environments. To sum up, here's what needs to be done by those wishing to not be an arc flash statistic. Conduct an arc flash study, obtain a permit, wear the correct PPE, use insulated tools, and keep your supervisor aware with safety briefing. And don't act like Scotty here. That is it from us. We really appreciate the opportunity to share about our work at the Great Plains Waste Management Conference, and we welcome any questions. Feel free to email us if you like. Thank you very much.